Welcome back. Our last video covered regularization and cross-validation. And in this video and the rest of the videos in this series, I wanted to showcase recent papers that have implemented machine learning methods to improve econometric analysis. And the first paper has to do with how we account for unobserved heterogeneity in nonlinear models. And this paper leverages k-means clustering to assist in that endeavor. This is the cover page of the paper. It's written by Stéphane Bonhomme, Thibaut Lamadon, and Elena Manresa, and it's published in Econometrica in 2022. And the title is Discretizing Unobserved Heterogeneity. And the setting is a panel data model where the unobserved heterogeneity is continuous in the population, but they're going to approximate it with a discrete distribution, which they're calling the group fixed effects, or GFE. And they propose a two-step algorithm to handle this. In the first step, they're classifying units into groups using k-means clustering. And then in the second step, they're estimating the model given the groups that they got from step one. And just to note, this is different than a finite mixture model where we assert from the outset that there are only a finite number of groups. In this case, the heterogeneity is continuous, but we're approximating it via the group fixed effects. And another nice thing about this compared to the finite mixture models is that we don't have any joint estimation that we're having to deal with. And this method also handles both time invariant and time varying unobserved heterogeneity. So how does this GFE compare with the random effects that we encountered with the EM algorithm or just plain old fixed effects? Well, the random effects is nice, and we could use them in both the EM and the MM algorithms, as we talked about earlier. But the efficiency requires distributional assumptions that may or may not hold. And in particular, we have to specify assumptions about the distribution of the unobserved heterogeneity. And if those distributions are wrong, then we can get a bias on all of our estimates. If we just want to do regular fixed effects, that's highly flexible, but then it suffers from a problem called incidental parameters, which is the case when nonlinear models try to have a fixed effect in them. And the reason that that's a problem is because the fixed effect can't be eliminated using the within transformation. And so if I let my sample size grow to infinity, then I'm going to get an infinite number of parameters that I have to estimate. And that's a problem. That's why we call it the incidental parameters problem. So the bottom line is I have too few data points to estimate the fixed effects, and that's going to lead to a bias in the estimate. The group fixed effects tries to play the middle ground on both of these. So it's basically fixed effects logic, but with a dimensionality reduction. And if we just say that there's some finite number of groups that's much smaller than n, then if we let n to infinity, then we're still going to get the same number of groups. So that fixes the incidental parameters problem. And there's also no distributional assumptions that we're imposing. And so we kind of get the best of both of these. The only downside is that we have a continuous unobserved heterogeneity distribution that we're having to treat as discrete. And there's two main assumptions that go into using this model. So one is that there's a low dimensionality to the types. So we just kind of covered that already, that even though I have continuous unobserved heterogeneity, that's all driven by some small set of latent characteristics. So this is not unlike the factor model assumptions that there's some low dimensionality driving the unobserved heterogeneity. It's not exactly the same, but it's not that different. So an example might be that heterogeneity in worker productivity and firm quality is both driven by some single match type between the two. And we can also handle time varying effects through a nonlinear factor structure if we want. So that basis is there. The other main assumption is that the types are learnable, just means that we can identify the types through the data that we have. So if I see somebody who persistently has a much higher wage than their observables would imply, then that must mean that they're overly productive. And so I should assign a high group fixed effect to that person. Another example is with serial correlation and choices, like we talked about with the mixed logit model way back when. And we can use this approach in a dynamic discrete choice model if we want. We can basically separate the likelihood of choices and state transitions and outcomes conditional on the group fixed effect. And if we assume that the likelihoods are additively separable given this group fixed effect, that's very similar to the situation with the EM algorithm that we talked about. And this requires strict concavity of the likelihood in alpha, but that's not a very limiting requirement because logit and probit and Poisson and Tobit and a bunch of other models satisfy that. Now let's talk a little bit about bias and inference. So there's two sources of bias in this group fixed effects model. One source is the incidental parameters bias that plagues the regular standard fixed effects in nonlinear models. And the second is the approximation error because we're assuming the true heterogeneity distribution is continuous, but we're discretizing it into discrete groups. And how do we correct this bias? Well, there's something called a half-panel jackknife, and we'll be seeing this in future videos in this series about how we overcome the bias from that machine learning algorithms bring into the econometrics. But basically, we're going to estimate our model on 3 different samples, first on the full sample, then on 2 halves of a sample. And then we're going to combine them as is written in this formula. And this BR means bias reduced. And that's going to allow us to get estimates that are free from the bias that we talked about up above on this slide. And then finally, you might be wondering, well, how do I get the number K for my number of groups? Well, they have a data-driven rule in the paper that's going to be optimal from the standpoint of this bias that's on this slide. There's also some extensions to this. So we can include covariates in that first step k-means clustering. So basically we would be doing a regression and then using the residuals from that regression to do the k-means clustering. We can iterate on a model if we want to impose or allow the structure of the model to provide more information. This has a flavor of the EM algorithm, but is simpler, but it's a good starting point. And then we could also do two-way grouping if we want. And I don't want to say much more than this, but this is a very useful paper in general. And so this is an example of how we can bring these machine learning principles in to econometrics and get a more tractable result or an algorithm or a method of econometrics that's more tractable as a result of getting the good parts of the machine learning into our analysis. Up next, we'll talk about how we bring machine learning into sample selection correction models. And we'll be looking at one of my papers that I've published in the recent past. So I hope to see you in the next video.